Very pleased to host this session for the Time Series Analysis and Forecasting Society. If you're aware, this is like a regular session for time series practitioners and experts. I'm delighted to have here with us today Max and Azul from Nixtla. You probably have already heard about all the amazing work that Nixtla is doing. So today they're going to be talking about TimeGPT. So before we start, I just wanted to kind of say a couple of words about TAFS. So basically, this is, as I mentioned, is a society for researchers, practitioners, and other stakeholders who are interested in time series analysis and forecasting. The objective of this series is to invite experts, academics, and researchers to discuss interesting problems, research, and solutions. And also for us to learn jointly, being able the community to learn about the innovations, real world applications and problems, both from kind of research perspective and also applications. So I would like to thank our sponsors, which is Talent Garden and Quantix. Quantix is a pioneering demand solution and AI platform. It's a startup based in Austria. So if you're interested in, or your company is interested in the solutions using AI for demand planning, very innovative solution, check it out, right? So without further ado, I'll pass it over to Max and Azul. I don't know, Max, do you prefer to have questions at the end or this throughout, and I can sort of monitor the chat for you guys to sort of also ask the questions?
I think if we can collect them and at the end have an open discussion, that would be amazing, because maybe some of the questions get answered through the presentation.
Fantastic, sounds good. So without further ado, then to you, Max and Azul, please.
Thank you so much, Valerie. It's good to be here with you, and also thank you to TAFS and to Rasul for the invitation. This is the second time that we have been here, and we are extremely proud to be speaking today, and also extremely happy. This is one of the venues that we like speaking the most. Normally, you have a lot of, as Valerie said, time series experts and practitioners. So we prepared a little presentation for you about, of course, TimeGPT, but also a little bit about Nixtla to begin with. So today, the topic is time series forecasting and what's now the trend of so-called generative AI or foundational models, or to be less hypey, pre-trained zero-shot models. For those of you who don't know Nixtla is a time series startup. We were the first startup that started focusing entirely on forecasting algorithms, and we identify as a time series research and deployment company. There are two big components to Nixtla. One is the open source time series ecosystem that we have developed, the Nixtlaverse, and the other is the commercial solution that we have been developing as a company, namely TimeGPT, which is an enterprise product. If you want to get free credits to test, to play around with TimeGPT, just write us an email. All members of TAFS, all participants of this conference can get as much free credits as you want, so you can start testing and playing around with it. But on the other side, we have also always supported the possibility for practitioners to develop their own forecasting pipelines. We have spent a lot of time and effort creating what's now probably the most comprehensive open source time series ecosystem, and you can use all the libraries without paying one single dollar. All of those are MIT licensed, so you can use them in your companies without any problems. Regarding the Nixtlaverse, we are very happy to announce that in the next couple of weeks, we will be releasing some new features for practitioners. We are including new models, from classical statistical models like the TBATs to new developments like TS mixers, TimeLLM, and others. We've also been working on our documentation. Now we support this intelligent chat, where you can ask things. How do I perform cross-validation, for example, and it's gonna use an LLM to read through the documentation and give you the right answers to use a cross-validation, for example, in the different libraries, neural forecast, ML forecast, stats forecast. So play around with it, tell us if this is helping you, and hopefully you enjoy this. But we have also been working on a utils forecast and core forecast to, for example, port some pre-processing steps into C++, making it extremely fast and extremely efficient. So the message here is that we are, of course, very interested in pushing the agenda of foundational models, in the sense that that is our commercial business model, but we are also extremely committed to the development of the open source and strengthening the community and creating great tools for you. Another important commercial for us, we are very big on the agenda of inclusion and diversity. We are proudly founded by members of the Latinx and LGBTQ+ community. We believe that diversity not only enriches algorithms, and that's something that we found while training TimeGPT, is not only the amount of data, but also the diversity of data that we have. So we are also pushing that agenda in team and community. The other commercial is we're very happy now that, thanks to the support of communities such as staffs and thought leaders, we have been implemented in many different companies in production-ready systems. We're now being used in many of the top companies in the world. We have more than 8,300 stars in total. The libraries have been downloaded more than 1 million times. And we're also very happy and proud to be contributing to the community, in the sense that all time series libraries rely in some sort or another on Nixtla. So Darts, PyTorch Forecasting, SKTime, GlueOnTS, SKForecast, all of those use Nixtla or one of the libraries of Nixtla as a dependency. So that's also something that we are very happy about. And now, coming to the main topic of today, one of the things that we realized while developing all these libraries and speaking with some of the brightest minds in the field is that forecasting is still hard, confusing, and expensive. So most companies still struggle to form a sophisticated team that is able to understand the intricacies of the field, that is able to distinguish when to use statistical machine learning, deep learning models. And there are a lot of different steps that you have to take into account when building these production-ready pipelines. So when we were thinking about this, a couple of years ago, when we started thinking about this, the whole OpenAI revolution happened. So we became very excited about the possibility of creating something similar for our field. We became very excited about trying to solve the problem of having pre-trained models for practitioners. And that's when we started researching TimeGPT. And that's also when we published the first foundational model, TimeGPT, which we are very proud. Like 6 months after Amazon published Chronos, and you have seen all the others, Momentum and TimeLLM, Llama, but it was, I think, incredible, and we're very happy about that. A lot of months ago, like a small company of 4 team members published that paper. But without further ado, and to deep dive into the model, I'm very proud to introduce my co-founder, Azul. She is the first author and one very important mind in the creation of TimeGPT. So she's going to be speaking with more depth about the model and about the comparisons, and I'm very happy to switch to her.
Thank you. Thank you so much. Thank you. Thank you so much. Thank you so much, Max, and thank you so much, Valerie, Rasul, and Tabs for having us here again. You are really excited to be here for the second time. So let me share my screen. So as Max mentioned, in our daily to daily practice in forecasting, we realized that the practice is extremely hard, confusing, and expensive because it involves a lot of different steps. No, at the beginning you need to start cleaning the data, after that, if you are using, for example, a machine learning model, you need to perform feature engineering. You need to create the lags or transformations of the lags to fit to the model. And since we have a lot of different options to model our time series, you need to select the best model. And one approach is by using cross validation. And since you probably are fitting a lot of different models and using a lot of different cross validation windows to assess the performance of them, obviously you need to parallelize the processes because you want the forecast to be really like in a small amount of time, right? So you need to parallelize that process. And after you are happy with the best model that you choose, basically you need to deploy the model, and that step involves a lot of different sub steps. First, you need to choose the right infrastructure. For example, you need to decide where the model will be deployed in Azure, in AWS, maybe in your own infrastructure. And after that, you need to actually deploy the model or a combination of them. For example, if you realize that the best model is an ensemble of certain models, you need to deploy that ensemble. And after that, you also need to monitor the deployment for you to see what's happening in terms of the performance of the model in real examples, in lifetime series observations, but also in terms of scalability of your model. If you have a lot of different time series, obviously you need to monitor the deployment to see if there is some improvement that you can do to have the forecast more rapidly. Just to give you an example of the complicated things that the forecasting field and deploying forecasting models involves, let me talk a little bit about deep learning versus statistical models. And basically, we did this benchmark against different models in the M3 dataset. And this experiment was inspired by one of the papers recently released by Makridakis. Basically, in that paper, Makridakis explained and showed that a combination of different deep learning models outperforms statistical baselines and also deep learning baselines. So, for example, in this image, we have the three frequencies of the M3 dataset: yearly, quarterly, monthly, and other. The model proposed by Makridakis and co-authors is the ensemble deep learning model that basically in all of the frequencies has the best performance, and also they included different statistical benchmarks and deep learning benchmarks. For example, Autoarima, WaveNet in the side of deep learning, also dynamic optimized theta, and so on. And that paper raised the question: what happens when you use different statistical methods and ensemble them to produce forecasts? And then we realized that one statistical ensemble, the combination between Autoarima, auto complex exponential smoothing, auto ETS, and dynamic optimized theta, had a really good performance in comparison with other deep learning models, and also against the ensemble that Makridakis proposed. As you can see in the graph, the statistical ensemble that was run and proposed also in a paper has better performance that, for example, n bits, even one transformer in the case of yearly, but that result also is shared with other frequencies. For example, in this case, the statistical ensemble has better performance than feed forward, which is basically fully connected neural network. And also in this case, for example, in other frequencies, the statistical ensemble has better performance at n bits, and also the deep learning ensemble proposed in their paper. And we think this is amazing because at the end of the day, deep learning involves a lot of different complexities around training the model, because if you want to train them efficiently, you need to use GPU, so you need to have the right infrastructure, but also it involves a lot of hyperparameter optimization, because at the end of the day, deep learning methods rely lots on the hyperparameters. So you need to train them in a right infrastructure, but also you need to perform hyperparameter selection, and that involves a completely complex pipeline that involves several steps. And of course, you need a lot of time to see the results. Here, for example, is a comparison of the computational complexity of a statistical ensemble, which was executed using a stats forecast, our statistical library. And as you can see, in terms of relative computational complexity, which is basically the comparison against the time that takes a decisional naive to be fed. And if you compare that statistical ensemble against the other deep learning methods, including the ensemble that Makridakis and co-authors proposed, you can see that the time in minutes explodes. The statistical ensemble only took around 6 minutes, but the ensemble took around 20,000 minutes. And that complexity, that computational complexity, also translates to costs in terms of the infrastructure that you are using. And as you can see, the cost for the statistical ensemble was less than $1, but you need to spend $1,000 if you want to create a deep learning ensemble. So in terms of complexity and in terms of costs of the infrastructure, it is probably a good idea for this particular data set to use a statistical ensemble that will have a comparable performance in terms of accuracy, but it will be a lot less expensive. So to reduce the complexity around deploying and monitoring and using deep learning models in production, one solution that recently has been developed is the idea of foundational models for time series forecasting. And it is the same idea as in LLMs. You have a huge data set of data, and then you train a deep learning model, in particular a transformer-based architecture on that huge data set, and then you can use the pre-trained model to produce forecast. So basically, you don't have to train the model on your own data. You basically just need to make inference on the pre-trained weights, and you will have, if everything works as expected, good performance on your own data. So that's the main idea behind these foundational models. How do we formalize this idea in mathematical terms? So basically, you can think a forecasting model as a function that basically considers a feature space, which is basically the time series. And the time series, the function looks at certain timestamps in the past of the time series, and then produces the forecast to another space. And one interesting thing about this forecasting task objective is that we are not only interested in estimate point forecast, but also we are interested in getting the whole distribution of the forecast. In other terms, we are not only interested in forecasting one point into the future, but we are interested in try to estimate different scenarios in the future. And this is really important because in some practical cases, you don't need to estimate the mean of the forecast, but you are interested in, for example, a particular quantile or a particular percentile. In other terms, you want to create prediction intervals because at the end of the day, if you have a whole distribution of the future, you can take better decisions based on that. For example, reducing minimizing the expected error or the expected output of the model. And basically, a foundational models is a pre-trained model on a usually large source data set, and that pre-trained model, it's good on new forecasting task with a different target data set. And obviously, that definition raises the question, in what target datasets the model could be good, or could have a good performance. So basically, we in a recent paper that we are about to publish, we are proposing this distance between two datasets, two time series datasets. And basically, this definition comes from the structure that deep learning models utilize to produce forecasts. So basically, a deep learning model in the current state of the art takes historical values, for example, which is known as input size. So basically, if you have a time series, the model will create different windows of size, input size plus horizon, and will try to minimize the error metric on the horizon part of the window using the previous lags to create the forecast. So at the end of the day, the model is looking at different windows of the different time series. So the distance definition presented here comes from that general idea. Basically, if you want to compare the distance between two data sets, you need to compute all the windows in both data sets, obviously with the same input size and output size or horizon, and then you can compare those windows against each other. And with that, using a particular metric, in this case, we are using our RMSE. Basically, you can compute the distance between those data sets. And obviously, if that distance is small, you can expect that the model pre-trained on the target data set will have a good performance on the other data set, right? Yeah, that's the idea that follows TimeGPT-1, which is the first foundational model for time series forecasting, and it is the first in two senses. It is the first that was released, and also the first one that it is already available to use in production environments. Basically, TimeGPT-1 is deployed through an API. If you want to use the API, of course, you can write us. But in fact, a lot of different companies have been used TimeGPT-1 in production environments. So it is ready to produce forecasts, to take decisions. And in that sense, it is also the first foundational model in production for time series forecasting. And the idea is that we trained or we pre-trained TimeGPT-1 on more than 100 billions of data points from different domains. And this is really important because while we were developing TimeGPT, we were very skeptical about the success of the idea and the success of the model. So basically, we approach this task very, very empirically, in the sense that we didn't have like a target or like a agenda behind, for example, using deep learning models or or sorry, I think okay. Deep learning models or statistical models, it was very, very empirical. Like, we had this idea and we expected to work, but we didn't know if it would work, right? So basically, it was amazing to see the results, but because we didn't expect that. But yeah, this is the main architecture behind TimeGPT-1. Basically, we collected a lot of different data sets ranging from finance, electricity, web traffic, retail, tourism, IoT, healthcare, transport, economics. And this is very important because while we were developing TimeGPT-1, we realized, as Max mentioned before, that it is important the amount of data that you have, but maybe it is more important the diversity of the data that you have. And this is really important because, for example, a very dummy example, you have one specific time series. Of course, you can replicate that time series, and then, I don't know, you can create a data set with billions of time series, but the subjacent process is the same, because it is the same time series repeated a lot of times. And obviously, if you have that data set and you pre-train a model, obviously the model will not learn anything besides the structure of that particular time series. So this dummy example is just to make the point that it is important the amount of data that you have to pre-train a model or to work on foundational models for time series forecasting, but it is also very important the diversity of the data. And with that diverse set of data, we trained this transformer architecture. And basically, once you have new data, you can just make an inference on that. And currently, TimeGPT-1 supports multivariate forecasting. Also, you can compute prediction intervals. Of course, you can produce quantile forecasts. You can fine-tune the model on your own data, and you can perform anomaly detection, which are different use cases that we have seen in real applications. And this is idea behind the inference phase of the model. Basically, you have a target variable that you want to forecast. And of course, you can have different exogenous variables that can be dummy variables or continuous variables. And then you can pass those variables to the model, and you will have the forecast, including an estimate of the distribution of the forecast. TimeGPT-1 offers accurate predictions, and it is orders of magnitude faster compared against traditional solutions, but also sophisticated methods, such as deep learning methods or machine learning-based methods. And of course, it is also fine-tunable in custom data. But here are the most important questions in our mind. And basically is, how does TimeGPT-1 compare against statistical models, machine learning models, and deep learning models but also we are very interested in understand how those TimeGPT compare against, for example, AutoML solutions out there. Currently, the different clouds, namely AWS, Azure, and Google, all of them have their own forecasting AutoML solution. So it is better than GPT-1, or those like pipelines, AutoML pipelines, have better performance. And the final question is, how does TimeGPT compare against other foundational models? And recently, this is a really important question for us because we have seen a lot of new developments in the field in this direction. So we are really eager to understand what's the performance in terms of course of accuracy, but also in computational complexity. So to answer this first question, here's the main table of our paper. And basically in the paper, we compare TimeGPT-1 with zero-shot inference. This means that the model never saw the data. The data was just used to produce the inference. And we compare that inference phase against different benchmark models. For example, the most basic ones, the zero model, which basically produces zero as forecast, but also the historic average and also the seasonal naive model. And after that, we compare TimeGPT-1 against more sophisticated statistical models, namely the theta method, the dynamic optimized theta, ETS, complex exponential smoothing, among others. And then we compare against LightGBM, which is a machine learning model, but also we included traditional deep learning models in the field, for example, LSTM and DeepAR, but also more sophisticated ones, such as TFT, which was developed by Google, and NHITS, which was developed by Nixtla. And as you can see in the table, we compare those performance for different frequencies, in particular monthly, weekly, daily, and hourly. And in terms of relative May, which is basically the division between the May of the particular model compared to the May of the seasonal naive model. In terms of relative May and relative RMSE, for monthly and weekly, TimeGPT-1 has the better performance. In terms of daily, has the second best performance, and it is also very competitive in the hourly case. And we think this is amazing because at the beginning we didn't expect that, and second because TimeGPT is very fast, and in particular because these are zero-shot forecasts. Basically, the model never saw that data, even for fine-tune the model. And obviously, we used a lot of data for this benchmark, more than 300,000 time series. And we used the Nixtla to perform these benchmarks. And this is, I think, very important because all of the libraries, stats forecast, ML forecast, and neural forecast, were used in this evaluation. And during this evaluation, like we realized that the distributed capabilities of the Nixtla were really necessary to create this benchmark. So we think this is very exciting. So to answer the second question, how does TimeGPT-1 compare against AutoML solutions? We recently did this comparison against Azure AutoML. in this comparison, we also use the zero-shot inference capabilities of TimeGPT. And in summary, TimeGPT outperforms Azure AutoML by 12% on May and RMSE, and by 10% in Maze. And which is also very exciting is that it is 300 times faster compared to Azure AutoML across the frequencies that we just discussed: hourly, daily, weekly, and monthly. We did this analysis using 3,000 random time series of our initial comparison. We use this small amount of time series because, as you can see, Azure AutoML takes too long to run. So basically, we limited the scope of the experiment to prevent the cost of AutoML to explode. So basically, we limited the experiment. They were random time series, so we think these results are in some way representative of the performance of both solutions. And one important thing about this experiment is that we used the production API of TimeGPT. So basically, we used our SDK. I'm gonna show you the code in a couple of minutes. But we used our SDK, and we did real-time inference, and yeah, I think that's exciting. Let me show you the code. Here we have different experiments. All of the experiments presented here are reproducible. So basically, here you can see the Azure AutoML comparison. Here we have a lot of different details that you can explore. But one thing that I wanted to show you, to also make the point of the complexity around the different tools that we as forecasting practitioners have. Let's take, for example, Azure AutoML. To use Azure AutoML and to produce forecast using Azure AutoML involves, again, a lot of different steps. So, for example, the first thing you need to do is to handle the AutoML forecasting solution in particular, because as a complete machine learning product, Azure has a lot of different models and a lot of different ways to handle machine learning models. So you need to pass your subscription ID, your resources, your workspace, and also you need to create these ML clients to interact with the cloud. You need to get like the train component, but also the inference component. And to produce the forecast, you need to define what cluster are you going to use, what is the primary metric that you want to optimize, the max tries that you want to keep, if you want or not enable early stopping, the max nodes of your cluster, if you want to retain the favorite model, the forecasting mode, if it is rolling or something else. So the forecasting pipeline is really like complex. And one important or one interesting thing about this pipeline is that it works in two steps. At the beginning, you upload your data. As you upload your job, you basically tell Azure, produce forecast of this data. So basically, you upload your data, you upload your job, and the cluster will be working like that, right? And once the process is finished, then you need to recover those forecasts. So basically, you need to create like a particular module to retrieve the forecast, and yeah, it involves a lot of different steps. Behind the scenes, Azure AutoML fits a lot of different models and then selects the best one for each time series. It is a kind of like an ensemble, and obviously you can select like the kind of ensemble technique that you want to use, but it is a really complex pipeline. And let me show you the difference against TimeGPT. With TimeGPT, you only need to instantiate your class. TimeGPT, you need to call the forecast method on your own data, and immediately you will have the forecast. You don't have to wait a lot of time to get the forecast. Basically, you send your data, and immediately you will have the forecast. And it only takes like, I don't know, 10 lines of code. So basically, TimeGPT reduces the complexity associated to deploying a lot of different models, waiting a lot of time to get the forecast and so on. So basically, that's the answer against how does TimeGPT 1 compare with AutoML solutions out there. We are, of course, working on making some benchmarks using Amazon Forecast, which is the AutoML solution for forecasting of AWS. And also, we are working on Google, in particular, Vertex AI. We already have like these benchmarks, but against the open source ecosystem, the Nixtla, but we are working on including TimeGPT as well. And the next question is, how does TimeGPT 1 compare against other foundational models? And one thing that we value a lot in Nixtla is benchmarking things. And before using more complicated models, always fit simple statistical models, and always fit the seasonal naive model. Because in practice, we have seen that seasonal naive is really hard to beat. It's like a model that has a really good performance. So always we benchmark our solutions against seasonal naive. And recently, a group of researchers released LAC-LAMA. And one interesting thing about LAC-LAMA is that they make the weights publicly available. So it's really easy to use and really easy to generate forecasts, because everything is open source, right? And basically, we compare LAC-LAMA against our implementation of seasonal AI, which is basically a really straightforward implementation. And we saw that for the most common used benchmarking data sets, namely M1, M3, M4, and tourism, seasonal naive exhibits 42% better performance in terms of May. And probably the most important metric, 16% better performance in terms of CRPS. And also it is 1,000 times faster than that foundational models. And we compared these two models using more than 100,000 unique time series, which corresponds to all the M competitions so far, except M5 and M6, and the tourism data set. And yeah, for LAC-LAMA we used a GPU infrastructure, obviously, because it needed that to be really efficient in terms of computational time, right? And probably one of the most interesting comparisons so far is against Amazon's Kronos, which is another open source foundational model for time series recently released. I think last week was released, and again we started benchmarking the model against seasonal naive, and what we saw is that Kronos has better performance than seasonal naive, and except of course in terms of computational complexity, because in some data sets, in particular the largest ones, it takes a lot of time. But we have seen in these experiments that Kronos has better performance. We are also finishing some comparisons, and we will release a public comparison soon. But in the meantime, we have seen this result, and I don't want to spoil anything, but also we have seen that TimeGPT has a better improvement compared to seasonal naive in particular data set. So stay tuned for the results. And as you can expect, the seasonal naive, it is a really fast model. So in terms of computational complexity, obviously, it is better. But Kronos has like a good performance in terms of computational complexity. Obviously, we think that this model, which was the largest one released by Amazon, it is not ready for like API workloads or API or production. Yeah, in particular for API, because obviously, if you submit a time series, you want the forecast to get the forecast almost immediately, which is how TimeGPT works. So, and this is also really important for us to share with you, because we deeply care about both things. It is really important, the accuracy, but it is also really important, the computational complexity, because at the end of the day, we want to make decisions as fast as possible. And in some scenarios, for example, IoT or real-time anomaly detection, obviously you need the model to be really, really fast to make decisions almost immediately. So it's something that we take very, very seriously, right? And we have different projects in the pipeline. We are working currently in this Kronos benchmarking thing, but also we recently included Time LLM, which is an interesting model because it is not like a foundational model for time series forecasting, but it uses like a pre-trained LLM to further improve or to train the model on time series data. So, for example, you can pass, I don't know, Llama, or you can use GPT-2 or even GPT-4, and the model is like a hybrid between these large language models and time series forecasting. And basically, the model computes different statistics of the time series and then prompts them to produce a certain kind of embeddings, and use those embeddings with a particular architecture for time series, and finally produce the forecast. It's really interesting, and we are also working on benchmarking that model. And another foundational model by CMU researchers, Momentum, will be included in the neural forecast library. So that's basically what is in the pipeline. We have a lot of different projects, but we think these are the most prominent ones right now, and in relation with with foundational models. But also we are working on expanding the Nixtla version. As Max mentioned, we are working really hard on improving the open source ecosystem. We are about to release TBATs in the statistical side, but we are also working on this auto version for machine learning models to select the best features of the machine learning pipeline, but also the best hyperparameters, obviously. And we are also working on expanding our hierarchical forecast library to be scalable. Currently, it has some kinds of limitation in the amount of data that you can pass and that you can use, because since it's a kind of multivariate problem, it involves a lot of computational complexity. So we are working really hard to improve the performance of the hierarchical forecast methodology. And of course, in terms of uh, future like features of TimeGPT, we will be including also hierarchical forecast inside TimeGPT. So this is also very exciting, because you just need to in the future you just will to upload like the hierarchical structure of your problem and your data. Basically, TimeGPT will give you the reconciled forecast and everything will work smoothly. So we are really excited about that. Maybe the TimeGPT 2 version will have this feature. And just to summarize, the results of TimeGPT-1 with this pre-trained model, with this pre-trained architecture, you don't need to be a machine learning expert to have highly quality forecast. And as I mentioned before, it is really easy to use if you are using different programming languages. Since it is an API, of course you can do it. Let me perhaps show you. But since it is an API, if you are using Node, for example, if you are creating this amazing web page where you show to your users like past sales, but also you want to show them like future sales, you can use TimeGPT, because since it is an API, you can embed your Node code there, and basically you here. I don't know if the token works, but you can use Node.js, and immediately you will have your forecast, and then you can paint the forecast in the data. But if you are using, I don't know, even PHP, you can use it. But if you are using Shell, also you can use it. I don't know, maybe even R. That we are really excited because we will be releasing a particular R SDK for TimeGPT. But the main idea is that you can use any programming language that you want to use or you have experience with. And we have this Python SDK that basically allows users to interact directly with the API without having to parse data to JSONs and worrying about like different parts of the pipeline that involves interacting with an API. So basically, you just need to import TimeGPT and call the forecast method on your pandas data frame, and then you will have your forecast as a pandas data frame, as the Nixtlaverse works currently. And also, if you have a lot of data, you can still use the TimeGPT SDK, because we have support for Spark, Ray, and Dask data frames. So if your data is huge, you can port it as a Spark data frame, and then you can pass that Spark data frame to the forecast method of TimeGPT, and the calls to the API will be handled concurrently. so you will get your forecast after the process ends. And if you are interested in using TimeGPT or try it out, please let us know. Join us to our Slack, and you can join the beta program there. Let us know. Also, you can send us a message through email. I think it's not here, but I think in some. I'm sorry about that. I just wanted to show the email. I don't know where it is, but it's ops at nixtla.io. And I think that's it from our side. Thank you very much, and happy forecasting.